The universe will end. But not tonight. Welcome to the Sleepy Lab. Tonight, we drift through deep time, through the slow cooling of stars, the silence after the last light goes out, and the quiet physics of how everything eventually comes to rest. Settle in. There is nowhere to be, and we have all the time in the universe. If this kind of journey helps you sleep, consider subscribing. One sleepy soul at a time. Now, let's begin. Somewhere above you, beyond the ceiling, beyond the atmosphere, beyond the reach of any telescope ever built, space continues, and continues, and continues still. The part of the universe we can observe, the sphere of light that has had time to reach us since the beginning, stretches roughly 93 billion light-years across, a distance so large it resists any honest attempt at comparison. And yet, as far as we can tell, that observable universe is only a fraction of what exists. The rest lies beyond a horizon we cannot cross, not because of any barrier, but simply because light from those regions has not had enough time to find us. The universe is approximately 13.8 billion years old. We know this not by counting backward through history, but by reading a kind of fossil light that still fills all of space. It is called the cosmic microwave background, the thermal afterglow of the Big Bang itself. In the earliest moments of the universe, everything was unimaginably hot and dense, a plasma so bright that light could not travel freely through it. Then, roughly 380,000 years after the beginning, the universe cooled just enough for atoms to form, and light was released. That light has been traveling ever since. It has stretched and cooled as space expanded around it, and today it arrives at our instruments as a faint, nearly uniform glow at a temperature of about 2.725 degrees above absolute zero. 2.725 degrees, almost nothing. And yet, that almost nothing is one of the most precisely measured quantities in all of science. It is the universe's oldest whisper, still audible if you know how to listen. But space is not standing still. Even now, as you lie here, the universe is expanding. Every galaxy not gravitationally bound to our own is drifting away from us, carried by the stretching of space itself. And that expansion is not slowing down. It is accelerating. Something is pushing the universe apart, growing faster with time. And physicists have given it a name, dark energy, though the name is more of a placeholder than an explanation. Dark energy makes up roughly 68% of the total energy content of the universe, and we do not know what it is. We know what it does. We can measure its effects with considerable precision, but its nature, whether it is a property of space itself, a field that permeates everything, or something else entirely, remains one of the deepest open questions in physics. 68% of everything. Unknown. There is something quietly humbling about that. The universe is mostly made of something we cannot identify, cannot directly detect, and cannot yet explain. The matter you are made of, the atoms in your body, the molecules in the air around you, the solid ground beneath your bed, all of that accounts for less than 5% of the universe's total content. The rest is dark energy and dark matter, two separate mysteries, both named for what they are not rather than what they are. And so the expansion continues. As space stretches, the cosmic microwave background stretches with it. The photons that make up that ancient light grow longer in wavelength, lower in energy, cooler in temperature. The 2.725 degrees we measure today was once much higher. In the early universe, the background radiation was hot enough to ionize matter, to prevent atoms from forming at all. Now it is barely above nothing, and it will keep falling. Not quickly. On any timescale a human mind can hold, the change is imperceptible. But over billions of years, the background temperature will continue to drop, approaching absolute zero with infinite patience, never quite arriving. Absolute zero is not a temperature the universe can reach. It is a limit, a boundary that can be approached asymptotically, the way a line can approach a curve without ever touching it. The universe will grow colder and colder, in smaller and smaller increments, forever drawing near to a stillness it can never fully achieve. There is something almost meditative about that. A universe in permanent, gradual approach, never arriving, always cooling. The expansion of space also has another consequence, one that takes longer to feel but is no less certain. Galaxies that are currently visible to us, the hundreds of billions of galaxies we can observe with our best instruments, are moving away. Most of them are already receding faster than light can cross the growing distance between us. We can still see them because the light they emitted long ago is still arriving, but the light they are emitting now will never reach us. The gap is growing too fast. In roughly 2 trillion years, a number so large it barely registers, every galaxy outside our own local group will have crossed beyond our cosmological horizon forever. The sky, to any observer who might exist then, would contain only the stars of the merged remnant of the Milky Way and Andromeda, and beyond that, darkness. No other galaxies. No evidence that other galaxies ever existed. The universe will have hidden its own history. But that is far ahead. For now, the universe is still relatively young. Stars are still burning. New ones are still forming, though less frequently than before. Star formation has been declining for roughly 10 billion years, and the universe has already produced about 95% of all the stars it ever will. The great age of star-making is behind us, though its embers still glow. And somewhere in all of that, in the 100 billion galaxies, each containing hundreds of billions of stars, many of them circled by planets, some of those planets sitting at the right distance from their sun, bathed in liquid water, wrapped in atmosphere. Somewhere in all of that, the question arises quietly: where is everyone? The universe is old enough and large enough and has been making stars and planets long enough that if life arises with any regularity at all, the galaxy should be full of it. A civilization that began even 1 billion years before our own would have had time, in principle, to spread across every star system in the Milky Way many times over. And yet, we look outward and find silence. We listen on every frequency we know how to monitor, and nothing answers. This is not a new observation. In 1950, the physicist Enrico Fermi reportedly raised the question during a lunch conversation, simply, almost casually, asking where all the extraterrestrial civilizations were. The question has carried his name ever since, and in the decades that followed, it has only grown more pointed. We have found that planets are common. We have found that the chemistry of life, carbon, water, organic molecules, appears throughout the galaxy. We have found nothing that looks like anyone else. The silence is not proof of absence, but it is a fact that requires an explanation. One framework that has guided thinking about this silence is called the Drake equation, a chain of probability factors, each one narrowing the estimate of how many communicating civilizations might exist in the galaxy right now. How often do stars form? How many have planets? How many of those planets could support life? How often does life actually arise? How often does it become complex? How often does it become intelligent? How long does it survive long enough to be detectable? Multiply those factors together and you get a number. But the honest answer is that most of those factors remain almost entirely unconstrained. Estimates range from nearly 0 to millions, depending on the assumptions you bring to the table. Some researchers have argued that the silence points towards something specific, that complex life may simply be extraordinarily rare. This is sometimes called the rare Earth hypothesis, the idea that the conditions which allowed life to flourish here were not typical, but deeply unusual. A large moon, stabilizing the tilt of the planet over billions of years, moderating the climate in ways that may have been essential. A position in the galaxy far from the dense, radiation-intense regions near the center, and a quieter neighborhood where long-term stability was possible. Plate tectonics, cycling carbon through the atmosphere and regulating the chemistry of the air over geological time, a process we have not confirmed on any other known world. Perhaps the silence is not a mystery at all. Perhaps it is simply what you would expect if the conditions for complex life are rare enough that we are, for now, alone. But there is a darker possibility. It is called the Great Filter, the idea that somewhere along the path from simple chemistry to a civilization capable of crossing interstellar distances, there is a step so difficult, so improbable, that almost nothing passes through it. A bottleneck so severe that the galaxy is littered with the quiet remnants of beginnings that never continued. The question that makes this idea unsettling is not whether the filter exists, it is where it sits. If the filter lies behind us, if the hard step was the origin of life itself, or the emergence of complex cells, or something else we have already passed, then perhaps we are genuinely rare, and the future is open. But if the filter lies ahead of us, if civilizations routinely reach something like our current moment and then fail to survive it, then the silence is not reassuring. It is a warning written in the absence of voices. The discovery of even simple microbial life on another world, Mars, or an ocean moon, would, under this framework, be deeply unsettling. Not because life elsewhere would be unwelcome, but because it would suggest that the origin of life is not the filter, that the hard step is still ahead. There are softer explanations. 2, some researchers suggest that advanced civilizations may simply be undetectable, that they transition into forms of existence that produce no radio emissions, no waste heat, no megastructures visible from the outside, that what we are listening for is not what they have become. Others propose something more deliberate, that civilizations capable of interstellar communication may choose silence, may actively avoid drawing attention, for reasons we can only speculate about from here. The universe may be full of listeners who have decided not to speak. We have been listening for decades, monitoring radio frequencies, scanning for patterns that could not be natural. In 1977, a signal was detected that remains unexplained, a brief, strong narrowband transmission that has never been repeated, never confirmed, never fully accounted for. It is called the wow signal. For the notation, a researcher wrote in the margin of the printout, "It may have been interference. It may have been something else entirely. We do not know." And not knowing is, in its own quiet way, part of the texture of this search. The silence continues. And perhaps that is where we leave the question, not resolved, but held. The universe is vast enough and old enough that the absence of a clear answer is itself a kind of answer. We are here. We are looking. And whatever is out there, or is not out there, the looking matters. But the universe does not wait for answers. It moves, slowly and without pause, in a direction that physics has been describing for a long time. There is a law, one of the most fundamental in all of science, that says disorder in a closed system always increases. That things tend, over time, toward their most probable arrangement. That heat flows from warm to cold, and not the other way. That structure, once lost, does not spontaneously return. This is the second law of thermodynamics, and on the longest timescales, it is the quiet engine driving the universe toward its end. The state that Law is pointing toward has a name: heat death, a condition in which the universe has reached maximum entropy, maximum disorder, and no further thermodynamic work is possible. No temperature differences left to drive any process. No gradients, no flows, no change. Not an explosion, not a collapse. Just an evenness so complete that nothing can happen anymore. Getting there takes time, more time than is easy to hold in the mind. Right now, the universe is still making stars, still burning hydrogen in 100 billion furnaces scattered across 100 billion galaxies. But that will not last. In roughly 100 trillion years, a number so large it has almost no meaning in ordinary terms, the last hydrogen-burning stars will exhaust their fuel and go dark. One by one, over timescales that dwarf the current age of the universe many times over, the lights will go out. Some will last longer than others. The smallest stars, red dwarfs, dim and cool and extraordinarily patient, burn their hydrogen so slowly that some will remain lit for 10 trillion years. Far outlasting stars like our Sun, which will exhaust its core hydrogen in another 5 billion years or so. Red dwarfs are miserly with their fuel in the best possible way, and in the very far future, they will be the last fires still burning in an otherwise darkening sky. But even they will end. After the last stars die, the universe will enter what cosmologists call the degenerate era, a long, cold epoch populated mainly by the remnants of what stars once were. White dwarfs, the dense, cooling cores of stars like our Sun, drifting through the dark. Neutron stars, the compressed remnants of larger stars that ended in collapse. And black holes, the deepest structures the universe produces, patient beyond any other measure. White dwarfs cool slowly, over trillions of years, radiating away the last of their heat into the surrounding void. Eventually, in principle, they become something that has never yet existed anywhere in the universe: cold, dark, inert objects called black dwarfs. The universe is not yet old enough for a single one to have formed. Every white dwarf that has ever existed is still warm, still faintly glowing, still somewhere on the long curve downward toward darkness. Inside a cooling white dwarf, something quiet and strange may happen. The carbon and oxygen at its core can crystallize, the atoms settling into a regular lattice as the temperature falls low enough, a structure resembling a diamond, but one the size of a planet, drifting alone in the dark between the stars. No light to catch it, no one to see it. Just the slow, patient geometry of matter finding its most ordered form in a universe that is otherwise moving steadily toward disorder. And the darkness deepens. The black holes remain. For a long time, longer than any era that has come before, they are the last large structures standing. Everything else has cooled, collapsed, or faded. The stars are gone. The white dwarfs have spent their last warmth. The neutron stars have grown cold and silent. But the black holes endure, patient in a way that strains any attempt at description. The largest of them will persist for something close to 10 to the power of 100 years. That number has a name, a googol, but the name does not help. It is not a number that corresponds to anything in ordinary experience. It is larger than the number of atoms in the observable universe, larger by so much that the comparison itself becomes meaningless. And yet, even across that span, the black holes are not truly permanent. They are only the slowest things to go. In the early 1970s, a physicist named Stephen Hawking worked through the mathematics of what happens at the boundary of a black hole, the event horizon, when quantum mechanics is taken into account. What he found was unexpected and quietly unsettling. Black holes, he concluded, are not entirely black. They glow very faintly with a kind of thermal radiation, not because anything escapes from inside them, nothing does, but because the quantum nature of space itself, at that boundary, produces a slow, steady leak of energy outward into the surrounding void. The radiation is almost unimaginably faint. For a black hole of stellar mass, the kind left behind when a large star collapses, the temperature of this radiation is far colder than the cosmic microwave background is today. In the current universe, such a black hole would actually be absorbing more energy from the background radiation than it emits. It would be, in a sense, gaining mass rather than losing it. Only in the far future, when the background radiation has thinned and cooled almost to nothing, will the slow evaporation begin to dominate. And then it will take roughly 10 to the power of 67 years for a single stellar mass black hole to lose everything, to radiate away, photon by photon, the last of what it is. The process accelerates toward the end. As a black hole shrinks, its temperature rises, and it radiates faster until the final moments arrive in a brief, quiet burst of energy. And then, nothing. Where the black hole was, there is only the faint warmth of its last breath, dispersing into the void. The supermassive black holes take longer still. The one at the center of a large galaxy, a structure millions or billions of times the mass of a star, would require something close to 10 to the power of 100 years to evaporate completely. A Google of years. The mind cannot hold this. It is better, perhaps, not to try. Better simply to let the number rest there, like a stone too large to lift, and move on. But eventually, even these will be gone. One by one, across timescales that have no human analogy, the last black holes will complete their slow evaporation. The final one will flicker out, not with violence, not with drama, but with a last quiet emission of radiation into a universe that is already, by then, almost entirely empty. And what remains? A diffuse gas. Photons, particles of light, drifting through an enormous, cold, dark space. Electrons and their relatives, the other leptons, scattered so thinly that the average distance between any two particles would be vaster than the observable universe is today. The temperature of this gas would be so close to absolute zero that the difference would be, for all practical purposes, nothing. No heat flows, no work is done, no structure forms. This is what physicists mean when they speak of the heat death of the universe, not a dramatic ending, not a fire or a collapse, but a final, stable stillness. The second law of thermodynamics, which has governed every process since the first moments after the Big Bang, reaches its conclusion. Entropy, the measure of disorder, of the spreading and equalizing of energy, has reached its maximum. There is nowhere left for it to go. In such a universe, there is no arrow of time. The sense we have that time moves forward, that the past is fixed and the future is open, is itself a product of entropy. It exists because the universe began in a state of extraordinarily low entropy and has been moving toward higher entropy ever since. That gradient, that slope, is what gives time its direction. In a universe at maximum entropy, the gradient is gone. Past and future become indistinguishable. Time, in any meaningful sense, ceases. And yet the universe does not end, exactly. It simply becomes a place where nothing happens. A vast, cold, dark, uniform expanse of near nothingness, persisting without change, without event, without witness. The heat death is not a wall that the universe runs into. It is a condition that the universe slowly, patiently settles into, the way a glass of water left on a table eventually reaches the temperature of the room, and then simply stays there. This is one ending, the one that current physics, taken at face value, seems most likely to produce. But there are others. Some of them arrive sooner, some of them are stranger, and some of them call into question not just the future of the universe, but the nature of what the universe is. The heat death assumes that dark energy, the force driving the accelerating expansion of space, remains constant. That its strength today is its strength forever. But dark energy is not well understood. Its nature is, as far as we can tell, entirely unknown. It fills roughly 68% of the total energy content of the universe, and yet no one knows what it is, where it comes from, or whether it changes over time. If it does change, if it grows stronger, then the ending may be different. More abrupt, more total. This possibility has a name, the Big Rip, and it begins not with a whisper, but with a slow, steady increase in the force pulling everything apart. In the current universe, dark energy is strong enough to accelerate the expansion of space on the largest scales, but gravity still holds galaxies, solar systems, and planets together. The Big Rip would occur if dark energy's strength grew without limit, eventually overcoming not just the expansion of space, but every other force in nature one by one. The largest structures would go first. Galaxy clusters, held together by the gravity of hundreds or thousands of galaxies, would begin to disperse. This would happen, in some models, roughly 200 million years before the final moment. On cosmic timescales, that is not long. It is, in fact, less time than has passed since the first dinosaurs walked the Earth. Then the galaxies themselves would be torn apart. Then solar systems, then planets. The timescales compress as the end approaches, the way the final moments of a piece of music can feel both slow and inevitable at once. About 2 months before the endpoint, planets and their orbits would be disrupted. In the final minutes, atoms themselves, held together by the electromagnetic force, would be pulled apart. Electrons stripped from nuclei broken into their components, the fundamental structure of matter undone. And then, nothing. Not the quiet nothing of heat death, but a more complete erasure. A universe in which even the possibility of structure has been removed. Whether the Big Rip occurs depends on a single number, the equation of state of dark energy, a measure of how its pressure relates to its density. Current measurements suggest dark energy behaves like a cosmological constant, unchanging over time. But the measurements are not precise enough to rule out a slow increase. The answer may come from future observations, or it may remain uncertain for as long as anyone is able to ask the question. The universe keeps its deepest secrets quietly. There is another possibility, one that does not end in fire or in tearing, but in something quieter and, in its own way, more complete. Physicists call it heat death, though the name is a little misleading because it is not hot at all. It is the coldest ending imaginable. To understand it, you have to hold in mind a principle that governs everything in the physical world, the second law of thermodynamics. It states, simply, that disorder tends to increase. A drop of ink spreads through water. A warm cup of tea cools to match the room. Energy, left to itself, flows from concentrated to diffuse, from ordered to scattered, and it never flows back on its own. The universe, as a whole, obeys this law. Right now, the cosmos is full of structure, stars burning at millions of degrees, planets orbiting in precise ellipses, atoms bonded into molecules, molecules folded into living things. All of this represents a kind of order, a low entropy state, in the language of physics. And all of it is very slowly unwinding. The stars will be the first to go. Over the next 100 trillion years, a number so large it has almost no meaning in ordinary life, the last hydrogen-burning stars will exhaust their fuel. One by one, across timescales that dwarf the current age of the universe many thousands of times over, they will cool and fade. The red dwarfs will be the last to go, small, dim, burning so slowly that some will persist for 10 trillion years. But even they will eventually go dark. And then the universe will enter a long, still era, populated by the remnants of stars, white dwarfs, slowly cooling over trillions of years. Neutron stars, dense and silent. And black holes, the longest-lived large structures the universe will ever produce, persisting for timescales written as 10 raised to the power of 100. That is a 1 followed by 100 zeros. It is not a number that maps onto anything human. It is simply vast. During this era, white dwarfs will cool so completely that they become dark, cold objects, what physicists call black dwarfs. None exist yet. The universe is not old enough. But inside those cooling remnants, something quiet and beautiful may happen. The carbon and oxygen at their cores can crystallize under immense pressure, forming a lattice structure not unlike a diamond. A diamond the size of a planet, drifting cold and dark through an empty universe, with no light left to catch its facets. And still, the black holes will remain. Stephen Hawking theorized that black holes are not entirely permanent. They emit a faint thermal radiation, so faint it has never been directly observed, and over immense timescales, this emission causes them to slowly lose mass. A black hole, the mass of a star, would take roughly 10 to the power of 67 years to evaporate completely. The supermassive black hole at the center of a large galaxy, something billions of times more massive, would take approximately 10 to the power of 100 years. And then it, too, would be gone. What remains after the last black hole evaporates is almost nothing. A thin, cold gas of photons and leptons, the lightest particles, spread across a universe so vast and so empty that the distance between any two particles would be almost incomprehensible. The temperature would be a fraction of a degree above absolute zero. Not silence exactly, but something close to it. A universe that has said everything it had to say and is now simply resting. This is heat death. Not a dramatic ending, not a rupture or a collapse, just a slow, patient approach toward a state of perfect uniformity. A universe in which every region is the same temperature, every gradient has dissolved, every difference has been erased. A state in which no thermodynamic work is possible, no engine can run, no star can burn, no thought can form. In such a universe, there would be no arrow of time. The sense we have that time flows from past to future, from cause to effect, is itself a product of entropy. It exists because the universe began in an extraordinarily ordered state and has been moving toward disorder ever since. In a universe at maximum entropy, that gradient disappears. There is no before and after, no direction, just an eternal, featureless present. And yet, even in that stillness, physics does not entirely stop. Quantum mechanics allows for fluctuations, tiny, random rearrangements of energy in the void, over timescales so long they require exponents stacked upon exponents to write. These fluctuations could, in principle, produce brief and improbable structures, a handful of particles arranged for a moment into something coherent. Most would be simple, fleeting, gone before they could mean anything. But over timescales of 10 to the power of 10 to the power of 56 years, a number that has no name, that no language was built to hold, random fluctuation could theoretically assemble something stranger, a momentary arrangement of particles complex enough to constitute a conscious observer, a mind, arising from nothing with no past and no future, experiencing a single instant of awareness before dissolving back into the void. Physicists call this a Boltzmann brain, after the 19th century physicist Ludwig Boltzmann, who first explored the statistical implications of entropy. It is not a prediction. It is a consequence, an almost impossibly remote one, of taking the mathematics of thermodynamics seriously across infinite time. Whether such a thing would constitute genuine experience, or something only resembling it, is a question physics cannot answer. But it is a quiet reminder that even at the very end of everything, the universe does not entirely close its doors. The end of the universe, then, is not a single moment. It is not a wall you could approach and see coming. It is a gradient, a slow, patient dimming that takes longer than any number has a name for. A process so gradual that no single moment within it would feel like an ending. Each era would simply give way to the next, the way evening gives way to night, and night gives way to a darkness so complete that the word night no longer quite applies. From the inside, if anyone were there to witness it, the universe would simply seem to grow quieter. Fewer stars, then none. Fewer sources of warmth, then none. The background hum of radiation cooling, degree by degree, toward a temperature that approaches zero without ever quite reaching it, because absolute zero, like a perfect horizon, can be approached but never arrived at. And somewhere in that long, slow cooling, the last coherent thought, if there ever is one, would dissolve. Not with grief, not with ceremony, simply because the conditions that made it possible would no longer hold. There is something in this that is not entirely bleak. The universe will have lasted. It will have produced, in its early and middle ages, a richness of structure and complexity that is almost beyond accounting. 100 billion galaxies, each containing hundreds of billions of stars, many of them circled by worlds. Some of those worlds perhaps harboring something that looked up and wondered. All of that will have happened. The heat death does not erase it. It simply follows it, the way silence follows music, without diminishing what the music was. The universe keeps its deepest secrets quietly. And in the end, it will keep its ending quietly too. But heat death is not the only ending physicists have imagined. There is another possibility, quieter in its arrival and stranger in its nature. It begins not with a force tearing things apart, nor with a slow cooling, but with a question about the ground beneath everything, about whether the universe is resting on solid foundations at all. Physicists describe the vacuum of space not as emptiness, but as a field. The Higgs field, which permeates all of space and gives particles their mass, exists at a certain energy level. That level feels stable. It has felt stable for nearly 14 billion years. But stability and true stability are not always the same thing. There is a difference between a ball resting at the bottom of a valley and a ball resting on a ledge partway up a slope. Both are still. Both appear settled. But one of them, given the right nudge, would roll somewhere else entirely. Current measurements of the Higgs boson, the particle that reveals the Higgs field's properties, suggest that our vacuum may be the ledge, not the valley, a state that is stable enough to have lasted this long, but not the lowest possible state, not the true ground. Physicists call this metastability. It means the universe may be resting in a configuration that is not, in the deepest sense, its final one. If that is true, then somewhere, at some point in time, perhaps already, perhaps unimaginably far from now, a quantum fluctuation could nudge the field over the edge. A small region of space would drop into the true vacuum, a lower energy state, a different set of rules. And from that point, a bubble would form. Not a bubble in the ordinary sense, not something you could see approaching. This bubble would be a boundary between two kinds of physics, the physics we know, and a physics in which the fundamental constants are different, in which the relationships between particles and forces are rewritten, in which the structures that make atoms possible, the precise balance of electromagnetic force, the specific masses of quarks and electrons would no longer hold. Inside the bubble, matter as we know it could not exist. The bubble would expand outward at the speed of light, not faster, exactly at the speed of light, which means it would be invisible in advance. No warning signal could outrun it. No light, no radio wave, no gravitational ripple could arrive before the boundary itself. The first moment of awareness would be the last moment of anything. There would be no experience of it, no transition. The bubble's edge would pass through a planet, a star, a galaxy, and the physics on the other side would simply be incompatible with the structures that had existed on this side, not destroyed in the way a fire destroys, replaced at the most fundamental level by a different set of rules that never permitted those structures in the first place. It is perhaps the strangest of all the endings, not because it is violent, but because it is so complete. Heat death leaves the universe intact, only emptied of useful energy. The Big Rip tears structures apart, but within the same physics. Vacuum decay would not tear the universe apart. It would rewrite it. And yet, the timescale for this, if it happens at all, is thought to be so vast that it dwarfs even the timescales of heat death. The metastable vacuum, if that is what we inhabit, appears to be extraordinarily patient. The numbers involved are difficult to write, let alone to hold in the mind. The universe could complete its entire current lifespan many times over, many billions of times over, before such a fluctuation became likely. So this ending, if it is an ending, belongs to a future so remote that it barely connects to anything we can picture. Still, there's something worth sitting with in the idea, the possibility that the universe is not resting on bedrock, that the laws of physics themselves may be contingent, not eternal truths, but local conditions, stable for now, in this particular valley of possibility. It is a quiet kind of uncertainty, not alarming, just present. There is another ending that belongs to an older chapter of cosmology, one that was once considered the most likely fate of all, before the discovery of dark energy changed the picture. For most of the 20th century, physicists were not certain whether the universe would expand forever. The answer depended on a single number, the total density of matter and energy in the universe, compared to a critical threshold. If the density exceeded that threshold, gravity would eventually win. The expansion would slow, stop, and reverse. The universe would begin to fall back toward itself. Galaxies that had been moving apart would begin, almost imperceptibly at first, to draw together again. The light from distant objects would shift from red to blue as they approached rather than receded. The cosmic microwave background, which has been cooling for nearly 14 billion years, would begin to warm. Over billions of years, the sky would grow brighter, not with new stars, but with the accumulated light of a universe contracting into a smaller and smaller volume. Galaxies would merge. Then the spaces between stars would shrink. Then the stars themselves would begin to collide and dissolve into a sea of plasma. the universe would return, in some sense, to something resembling its beginning, an extraordinarily hot, dense state, a mirror of the Big Bang, but running in reverse. This is the Big Crunch. And it would not be a gentle ending. It would be the most energetic event since the universe began, a compression of everything that exists into a singularity, or something near one. Whether physics as we know it could survive that moment, or whether the equations simply break down at the boundary, is not something current theory can answer. What we can say is that the Big Crunch now appears unlikely. The discovery in the late 1990s that the expansion of the universe is accelerating, driven by dark energy, shifted the balance decisively. A universe that is speeding up in its expansion is not one that is about to reverse course. The data, gathered from distant supernovae and the large-scale structure of the cosmos, point strongly toward continued expansion. But strongly is not the same as certainly. The precise nature of dark energy remains unknown. Its value could, in principle, change over time. Some models allow for it. And if dark energy were to weaken, or if our measurements of the universe's total density contain errors we have not yet detected, the possibility of eventual collapse cannot be entirely set aside. Current observations do not favor it, but the universe has surprised us before, and the humility of science includes leaving certain doors ajar, not because we expect to walk through them, but because we have not yet confirmed they are sealed. So the Big Crunch rests in the background of cosmology, not the leading theory, not the expected outcome, but a reminder that the universe's future is not yet written with perfect certainty, and that the forces shaping it, dark energy above all, are still not fully understood. The universe holds its trajectory loosely, and we, watching from one small moment near its beginning, are still learning to read the signs. Some ideas in cosmology do not predict an ending so much as a transformation. Cyclic cosmology is one of them. Rather than a universe that begins once and ends once, these models propose something quieter and stranger, that what we call the beginning was not a beginning at all, but a transition, a moment of rebirth in a sequence that may have no first chapter and no last. The universe, in this view, does not die. It turns. There are several ways physicists have tried to make this mathematically precise, and they differ in their details, but they share a common intuition that the conditions we associate with a Big Bang might be produced not from nothing, but from something that came before. One of the more developed proposals is called the ekpyrotic model. In this picture, our universe exists on a kind of membrane, physicists call it a brain, floating in a space with more dimensions than the three we can perceive. Parallel to ours, separated by a gap too small to measure and too strange to visualize, lies another membrane. The two drift slowly through this higher dimensional space, and occasionally, over timescales that dwarf even the age of our universe, they collide. When they do, the energy of that collision floods through both membranes. And what that energy looks like from inside one of them is something very much like a Big Bang. Matter and radiation fill the space. Temperature climbs to unimaginable heights. And then, as the membranes rebound and separate, the universe cools and expands. Structures form. Stars ignite. Galaxies gather themselves from the dark. Life, perhaps, arises in quiet corners. And then, over trillions upon trillions of years, it all grows cold and still, until the membranes drift close again, and the cycle turns once more. There is something almost restful in this picture, if you let yourself sit with it. Not an ending, but a rhythm. The universe breathing in and out across timescales so vast they dissolve any sense of urgency. The ekpyrotic model is not the consensus view. It faces real theoretical challenges, and the observational signatures that would distinguish it from a standard Big Bang cosmology are subtle and contested. But it represents a serious attempt to ask whether the universe might be older, in some sense, than its own beginning. And it is not the only such attempt. Roger Penrose, a mathematician and physicist whose work spans general relativity and the nature of consciousness, proposed a different cyclic framework, one he calls conformal cyclic cosmology. His idea begins with a question about the far future. In the heat-death scenario, the universe eventually reaches a state of maximum entropy. All black holes have evaporated. All matter has decayed or dispersed. What remains is a thin, cold, nearly featureless expanse of photons and leptons, drifting through a space that continues to expand. No clocks tick in this universe, because clocks require mass, and mass requires structure, and structure has dissolved. Without mass, without any massive particles at all, Penrose argues that the universe loses its ability to measure time in the ordinary sense, and in a precise mathematical way, a universe with no massive particles and a universe at the very beginning of a Big Bang share a kind of structural similarity. Both are, in the language of geometry, conformally equivalent. The scales are unimaginably different, but the shape, in a deep mathematical sense, is the same. And so Penrose proposes that the far future of one universe, cold, dark, emptied of everything but light, can be smoothly matched onto the beginning of the next, not through a collision, not through a bounce, but through a kind of geometric continuity. The end of one eon, as he calls it, becoming the birth of another. The new universe would not remember the old one, not in any ordinary sense, but Penrose suggests that something might carry through faint imprints, subtle patterns pressed into the fabric of the new universe by the final events of the previous one, the last evaporating black holes, the last concentrations of energy before the great dispersal. These imprints, he proposes, might be detectable, encoded as faint, concentric rings of slightly varying temperature in the cosmic microwave background, the thermal afterglow that fills our own sky. These have been disputed. Some analyses claim to find patterns consistent with Penrose's prediction. Others find the same patterns consistent with random noise. The question remains open, as so many questions at the frontier of cosmology do. But the idea itself is striking in a way that goes beyond the mathematics. It suggests that our universe may carry, written in its oldest light, a kind of memory. Not a memory that any mind could read, not a message in any language, but a structural echo of something that burned and faded before our Big Bang ever occurred. We are, perhaps, not the first chapter. We may not be the last. There is a quality to cyclic models that sets them apart from the other endings, the heat death, the big rip, the vacuum decay. Those are conclusions. They arrive, and then there is nothing further to say. But cyclic cosmology refuses the conclusion. It finds, in the apparent ending, the seed of a continuation. Whether that continuation is real, whether the mathematics describes something that actually happens, or only something that is mathematically possible, is a question physics cannot yet answer. The observations needed to distinguish between a cyclic universe and a universe that simply ends are extraordinarily difficult to make. The signals, if they exist, are buried in the faintest structures of the oldest light we can detect. And the theoretical frameworks themselves are still being refined, still being tested against what we know of quantum gravity and the behavior of space at its most extreme. What we can say is this: the universe does not obviously forbid a cycle. The laws of physics, as we understand them, do not rule it out. And the human instinct to find pattern and recurrence in the cosmos, to see the universe not as a single flame burning down, but as something that pulses, that returns, that instinct has found, in these models, a serious mathematical home. Not a certainty, not even a leading theory, but a genuine possibility held open by careful minds who have looked at the far future and the deep past and asked whether they might, in some quiet way, be the same moment. The universe holds its trajectory loosely, and we, watching from one small moment near its beginning, are still learning to read the signs. Perhaps there were other beginnings before ours. Perhaps the light now cooling in the oldest reaches of our sky carries the faintest trace of something that ended long before our stars were born. Perhaps the universe has always been doing this, turning slowly in the dark. And yet the turning does not go on forever in the way we might picture it. Even if the universe cycles, even if it breathes in and out across timescales that have no names, there is still the question of what can be seen, of what any observer, anywhere, at any moment, is actually able to know. Because the universe has a horizon, not a wall, not a boundary in space where something ends and something else begins, but a limit set by time itself. Light travels at a fixed speed. The universe has existed for a finite duration, and so there is a sphere around every point in space, around you, around every star, around every galaxy, beyond which light simply has not had enough time to arrive since the beginning. That sphere, for us, is roughly 46 billion light years in radius. Everything within it is, in principle, observable. Everything beyond it is not hidden by distance alone, but by time. The light from those regions is still traveling toward us. It will never arrive. Not because it is too far, but because the space between us and it is growing faster than the light can cross. This is one of the quieter implications of an expanding universe. Some galaxies are already receding from us faster than light, not because they are moving through space at that speed, nothing does, but because space itself is stretching between us and them, and the cumulative effect of that stretching, across billions of light years, adds up to a recession speed that exceeds the speed of light. Those galaxies are not violating any law. They are simply being carried away by the expansion of the medium they sit in, and the light they emit toward us will never close the gap. They are already, in a meaningful sense, gone. We can still see some of them. The light that left them long ago, when they were closer, is still arriving. We are seeing their past, but their present and their future is beyond our reach. And with every passing moment, more of the universe crosses that threshold and recedes into a darkness that is not dark because it is empty, but dark because it is unreachable. In roughly 2 trillion years, this process will be complete for everything outside our local group. The local group is the small cluster of galaxies we belong to. The Milky Way, Andromeda, a few dozen smaller companions. Gravitationally bound to one another, they will not be carried apart by the expansion. They will remain together. But everything else, the hundreds of billions of other galaxies now visible in our sky, will have receded beyond the cosmological horizon. Not destroyed, not gone in any absolute sense, simply unreachable and invisible and silent. Any civilization that exists 2 trillion years from now, looking out from whatever remains of a world, will see a sky with no other galaxies in it. They will see stars. If stars still burn, they will see the remnants of their own galaxy. but the vast cosmic web, the clusters and filaments and superclusters that we can map today across billions of light years. All of that will be gone from view, not because it ceased to exist, but because the universe will have stretched the evidence beyond recovery. And here's what sits quietly at the center of that thought. Those future observers, if they exist, will have no way of knowing that other galaxies were ever there. The cosmic microwave background will have redshifted into wavelengths so long they may be undetectable. The light from distant galaxies will have faded entirely. There will be no fossil record in the sky of the universe's larger structure. They will look out and see only their own small island of matter in an otherwise featureless dark. And if they are curious, if they build instruments and ask questions, they may conclude that the universe is simply this: one galaxy, alone, in an infinite and empty expanse. They will be wrong, but they will have no way to know that. We are fortunate, in a way that is easy to overlook, to exist now. In this particular window of cosmic time, when the universe is old enough to have formed stars and planets and the conditions for complexity, but young enough that the evidence of its full structure is still visible. We can see the shape of things. We can read the expansion in the redshift of distant light. We can detect the microwave afterglow of the beginning. We can map the large-scale structure of the cosmos and know, with reasonable confidence, that we are one galaxy among hundreds of billions. That knowledge is not permanent. It is a gift of timing. And even within our own local group, the sky is changing on timescales that feel long to us but are brief against the life of the universe. The Milky Way and the Andromeda Galaxy are moving toward each other. Andromeda is roughly 2.5 million light-years away, a vast distance by any ordinary measure. But the two galaxies are gravitationally drawn together, and they are closing that distance at roughly 110 kilometers per second. In approximately 4.5 billion years, they will meet. The word collision is technically accurate, but somewhat misleading. Galaxies are mostly empty space. The stars within them are so far apart that when two galaxies pass through each other, direct stellar collisions are extraordinarily rare. What happens instead is a long, slow gravitational dance. The two galaxies will pass through one another, distort each other's shapes, pull long tidal streams of stars out into space, separate briefly, and then fall back together. Over hundreds of millions of years, they will merge into a single structure. That structure will be an elliptical galaxy. Elliptical galaxies are quieter than spiral ones. The Milky Way, as it exists now, is a spiral, a rotating disk of gas and dust and stars, with active regions of star formation in its arms. Andromeda is also a spiral, but when they merge, the ordered rotation of both will be disrupted. The gas that fuels star formation will be consumed in a burst of new stars triggered by the collision, and then largely exhausted. What remains will be a large, roughly spherical cloud of older stars, slowly aging, with little material left to form new ones. Some have given this future galaxy a name, Milkomda, a quiet blending of the two names into one. It will be a large and ancient place, populated by stars that formed billions of years before the merger, now growing old together in a structure that no longer has the shape or the energy of its origins. The Sun, if it still exists in some form, will have long since ended its main sequence life by then. The Earth will be gone, but the stars that were once scattered across two separate galaxies will share a single gravitational home, and Milkomeda will drift on. Alone in an expanding universe, its companion galaxies long since carried beyond the horizon, its own star formation slowly winding down, its oldest stars cooling toward the long darkness that waits at the end of stellar time. It will be a remnant of something larger, a memory, in matter, of a universe that was once full of light and structure and the possibility of everything. The horizon will have closed around it, and it will continue quietly in the only universe it can see. Star formation has been declining for a long time now, not just in the future we have been tracing together, but already, in the present, in the universe as it exists tonight while you rest here. The peak of star formation passed roughly 10 billion years ago. At that time, galaxies were dense with gas, colliding and merging, their interiors turbulent with the raw material of new suns. Stars were being born at a rate that the universe will never see again. Since then, the rate has been falling. Slowly, steadily, like a tide going out so gradually that no single moment marks the turning. By the time our own sun formed, about 4.5 billion years ago, the universe had already passed its most fertile period. The sun was born into a cosmos that was already aging, already past the height of its creative power. And the numbers carry a kind of quiet weight. Roughly 95% of all the stars this universe will ever produce were already formed within the first few billion years of its existence. The remaining 5%, the stars being born now, the ones that will form in the distant future, are a long, slow afterthought, a fading continuation of something that already reached its fullness long before the Earth existed. The universe, in a sense, has already done most of its work. What remains is a gradual unwinding, a patient dimming of what was once a blazing period of creation. Milkomeda will inherit this, a galaxy formed from two, carrying within it the light of stars that were born in a more abundant time, stars that formed when the universe was younger and richer in the raw hydrogen that feeds stellar birth. Those stars will age inside Milkomeda, and new ones will form only rarely from whatever gas remains. Each new star, a smaller fraction of a diminishing reserve. The universe is not ending quickly. It is simply becoming quieter, one star at a time. And in that quietness, a question has lived for a long time. A question that was asked, as far as we know, during an ordinary lunch conversation in the summer of 1950. A physicist named Enrico Fermi sat with colleagues, and the conversation turned, as it sometimes did, to the possibility of life beyond Earth. And at some point, in a way that those present remembered as almost offhand, Fermi asked a simple question. Where is everybody? It was not a dramatic question. It was almost a practical one. The galaxy is old, roughly 13 billion years old. Old enough that a civilization arising anywhere within it, even billions of years ago, would have had time, more than enough time, to spread across every star system many times over. Even at speeds far below the speed of light, the mathematics of expansion across a galaxy are not prohibitive given enough time. And yet, no confirmed signal, no artifact, no visitor, no trace of anything that did not arise here, on this small planet, orbiting an ordinary star in a quiet region of the Milky Way. The silence is the paradox. Not the absence of life itself, necessarily, but the absence of any sign of it, given how long the galaxy has existed and how much time there has been for something to make itself known. This tension between the apparent likelihood of life elsewhere and the complete absence of evidence for it carries Fermi's name now, the Fermi Paradox, though it is less a paradox in the logical sense and more a deep, unresolved discomfort, a gap between what the numbers seem to suggest and what the sky actually shows. Some years after Fermi's question, a researcher named Frank Drake tried to give the problem a more formal shape. He constructed an equation, not to produce a definitive answer, but to organize the uncertainty, to lay out, in sequence, all the factors that would need to be known in order to estimate how many communicating civilizations might exist in the galaxy at any given time. The equation begins with the rate at which stars form in the galaxy, then asks what fraction of those stars have planets, what fraction of those planets could support life, what fraction actually develop life, what fraction of that life becomes intelligent, what fraction of intelligent life develops technology capable of sending detectable signals into space, and finally, how long such a civilization might survive and continue transmitting. Each factor is a question, and most of them remain, even now, only loosely answered. The fraction of stars with planets has become better understood in recent decades. Observations suggest that planets are common, perhaps the rule rather than the exception, but the fraction of planets where life actually arises, that number remains almost entirely unknown. We have one data point, this world. And one data point cannot tell you whether life is inevitable wherever conditions allow, or whether it is so improbable that it has happened only once in the observable universe. The later factors in the equation are even less constrained. The fraction of life that becomes intelligent, the fraction of intelligent life that develops technology, the lifespan of a technological civilization. These are not numbers that current science can pin down with any confidence. Estimates from different researchers, using the same equation with different assumptions, have ranged from nearly zero, suggesting we may be alone, to millions of civilizations active in the galaxy right now. The equation does not resolve the paradox. It maps it. It shows, with some precision, exactly where our ignorance lives, which questions we cannot yet answer, and how sensitive the final result is to each of them. A small change in the assumed probability of life arising from chemistry, or in the typical lifespan of a civilization, shifts the answer by orders of magnitude. And so the silence of the sky remains open to interpretation. Perhaps life is extraordinarily rare at some early step. Perhaps the origin of life from chemistry, or the transition from simple cells to complex ones, is so improbable that it has happened only a handful of times across the entire observable universe. In that case, the silence is simply the silence of an almost empty stage. Or perhaps life arises readily, but something else intervenes. Something that prevents civilizations from reaching the point of making themselves known across interstellar distances. Something that has, so far, stopped every one of them. Or perhaps the universe is full of life, and the silence has a different explanation entirely, one that has more to do with the nature of communication, or the choices civilizations make, than with their absence. None of these answers is settled. The Drake equation holds the question open, carefully, without forcing a resolution that the evidence does not yet support. And the universe continues its slow decline in star formation, indifferent to whether any of those stars ever warmed a world that asked questions about the others. The rate falls, the gas thins. The new stars come less frequently now than they once did, and somewhere in the long arithmetic of galaxies and time, the question Fermi asked over lunch remains exactly as open as it was that afternoon. Where is everybody? The sky does not answer. It only continues, quietly, to expand. One answer to the silence begins not with distance, but with conditions. It begins with the idea that life, not just any life, but the kind that builds and wonders and eventually reaches toward other stars, may require a combination of circumstances so specific, so layered, that the universe produces it only rarely, perhaps almost never. This is sometimes called the rare Earth hypothesis. It does not claim that life is impossible elsewhere. It claims only that the particular arrangement of factors that allowed complex life to emerge here may be far less common than we tend to assume. And when you begin to list those factors, the weight of them accumulates quietly. Consider the moon. Our moon is unusually large relative to the planet it orbits. Most moons in the solar system are small, captured objects, or the remnants of ancient collisions that left only modest companions behind. Ours is different. It is thought to have formed from a catastrophic impact early in Earth's history, when a body roughly the size of Mars struck the young planet and sent debris spiraling into orbit. Over time, that debris coalesced into the moon we see now. And the moon does something that may matter enormously. It stabilizes Earth's axial tilt. The Earth is tilted on its axis at roughly 23.5 degrees. That tilt is what gives us seasons. But without the moon's gravitational steadying influence, that tilt would not remain stable, it would wander. Over millions of years, it could shift dramatically from nearly upright to severely tilted, driven by the gravitational tugs of the other planets. A planet with a wildly varying axial tilt would experience climate swings of a kind that might be deeply hostile to the slow, patient work of biological complexity. Ice ages and heat ages cycling, not over tens of thousands of years, but over millions, in patterns too erratic for ecosystems to track. The moon holds the tilt steady. It has done so for billions of years. And in doing so, it may have given life on Earth the climatic stability it needed to move from simple to complex, from single cells to everything that followed. How many planets have a moon like ours? The answer, as far as we can tell, is not many. Then, there is where we are. The Milky Way is not a uniform place. Its center is dense, crowded, and violent, a region of intense radiation, frequent supernovae, and gravitational chaos that would sterilize most worlds before they had a chance to develop anything lasting. The outer edges of the galaxy are quieter, but also thin in the heavy elements that planets and life are built from. Those elements, carbon, oxygen, iron, the whole periodic table beyond hydrogen and helium, are forged in stars and scattered by their deaths. The outer galaxy has had fewer generations of stars, and so fewer of those elements. The Sun sits in a region sometimes called the galactic habitable zone, far enough from the center to avoid the worst of the radiation and gravitational disruption, close enough to the inner galaxy to have access to the heavier elements that rocky planets require. It is a quiet neighborhood, relatively stable, the kind of place where a star can burn steadily for billions of years without being disturbed by a nearby supernova or a close stellar encounter that might destabilize the orbits of its planets. Whether this position is rare is difficult to say with precision, but it is not obviously common. And then there is the ground beneath our feet. Earth's surface is not fixed. It is broken into great plates of rock that move, slowly, over the softer material beneath them. They collide and separate, building mountains and opening ocean basins, carrying the continents across the face of the planet over hundreds of millions of years. This process, plate tectonics, does something that may be essential to the long-term habitability of a world. It recycles carbon. Carbon dioxide enters the atmosphere from volcanoes. It dissolves in rainwater, forming a weak acid that slowly weathers rock. That weathered material washes into the ocean, where it eventually sinks with the ocean floor and is pulled back into the mantle at the boundaries of tectonic plates. There, it is heated and eventually returned to the atmosphere through volcanic activity again. This cycle acts as a thermostat. When the planet warms, weathering accelerates, pulling more carbon dioxide from the atmosphere and cooling things down. When the planet cools, weathering slows, allowing carbon dioxide to accumulate and warm things back up. Over geological timescales, it keeps the climate within a range that liquid water and life can tolerate. No other planet in the solar system is confirmed to have plate tectonics. Mars does not. Venus does not, or at least not in the same way. Whether other worlds and other solar systems do is something we cannot yet determine from the observations available to us. A planet without this recycling mechanism might drift toward a permanent deep freeze or a runaway greenhouse with no internal process to pull it back. Earth has been lucky, or specific, or both. And so, the rare Earth hypothesis assembles its case piece by piece. A large stabilizing moon, a quiet position in the galaxy, a carbon recycling geology, a star of the right size and temperament, a planetary system arranged in a way that shields the inner worlds from too many catastrophic impacts. Each factor alone might not be decisive, but together, they suggest that the path to complex life may be narrow enough that the silence begins to make a different kind of sense. And yet, even if complex life is rare, even if it arises only once in a billion worlds, the universe contains enough worlds that the number could still be large. The silence might still need another explanation. Which brings us to a quieter and more unsettling idea. Perhaps life does arise. Perhaps it reaches complexity. Perhaps it even reaches the point of technology, of communication, of looking outward, and then something stops it. Not something external, not a cosmic catastrophe that sweeps civilizations away from the outside, but something internal, some threshold in the development of a spacefaring civilization that is extraordinarily difficult to cross. This is called the Great Filter. The idea is simple in outline. Between the formation of a rocky planet and the emergence of a civilization that can make itself known across interstellar distances, there are many steps. The origin of life, the emergence of complex cells, the development of multicellular organisms, the evolution of intelligence, the invention of technology, the survival of that technology long enough to reach other stars. Any one of these steps could be the filter, the step that almost nothing gets through. If the filter lies behind us, if it is something we have already passed, then it may mean that one of those early steps is vanishingly rare. Perhaps the origin of life itself is the hard part. Perhaps the leap from simple bacteria to the complex cells that make up every plant and animal on Earth, a leap that took nearly 2 billion years and may have happened only once, is the step that almost never occurs. In that case, we are the survivors of an almost impossible sequence. The silence around us is the silence of a universe where the filter was crossed here and almost nowhere else. And that would be, in its own quiet way, a kind of answer. Not a comforting one, but an answer. The alternative is harder to sit with. If the filter does not lie behind us, if it lies ahead, then it means that civilizations like ours routinely reach this point and then do not continue. That the silence is not the silence of an empty universe, but the silence of one in which something, again and again, intervenes. The universe expands. The stars continue their slow decline. And the question of which kind of silence this is remains, for now, unanswered. There is a version of the silence that is almost peaceful. If the filter is behind us, if the hard part is already done, then the quiet of the cosmos is simply the quiet of a universe where life is rare, and we are among the few who made it through. But there is another version. If the filter lies ahead, the silence takes on a different quality entirely. It means that civilizations do reach this point. They develop language, and science and the ability to look outward. They ask the same questions we are asking now. And then, at some stage, not far beyond where we stand, something ends them. Not one civilization, not a few, but nearly all of them, again and again, across billions of years and hundreds of billions of star systems. The silence would not be the silence of an empty stage. It would be the silence after. What ends them is not specified by the hypothesis. It may be war. It may be the unintended consequences of technologies that outpace wisdom. It may be something we have not yet conceived of, some threshold that every sufficiently complex civilization eventually reaches and almost none crosses. The Great Filter, in this reading, is not a wall in the past. It is a wall just ahead, patient and invisible, waiting in the ordinary progression of things. This is why certain discoveries, which might seem like cause for wonder, carry a shadow beneath them. Consider Mars. Mars is a cold, dry world now. Its atmosphere is thin, its surface scoured by radiation, its liquid water long gone from the surface. But Mars was not always this way. Roughly 3 to 4 billion years ago, it had a thicker atmosphere, a magnetic field, and liquid water pooling in low-lying basins. The conditions, as far as we can tell, were not entirely unlike the early Earth. If life began on Earth under those conditions, it is reasonable to ask whether life began on Mars as well. And here is where the shadow falls. If we were to land on Mars or send the right instruments to the right place and find something, not a fossil of something large and complex, but something small, a microbial cell or the unmistakable chemical signature of ancient biology, something that said, quietly and without ambiguity, that life had started there too, independently, on a neighboring world, the implications would be profound. It would mean that life is not a miracle confined to one fortunate planet. It would mean that wherever the conditions are roughly right, life tends to begin. It would mean that the universe is, in some sense, full of life at its simplest level. And under the Great Filter framework, that would be deeply unsettling. Because if life starts easily, if it crosses the threshold from chemistry to biology whenever the environment allows, then the filter is almost certainly not in that early step. It lies somewhere further along the path, in the development of complex cells, perhaps, or in the emergence of intelligence, or, most troublingly, somewhere in the space between a civilization that can ask questions and one that can survive its own answers. The more common simple life turns out to be, the more the filter must be concentrated in the later stages. And the later the filter, the closer it is to us. So the discovery of a microbe on Mars would be, in the same breath, one of the most extraordinary moments in human history and one of the most sobering. We have been listening, in the meantime, for decades now. Arrays of radio telescopes have been pointed at the sky, scanning frequencies that a technological civilization might use to communicate across interstellar distances. The project has gone by different names and used different instruments over the years, but the underlying effort has been consistent, patient, methodical, and so far unrewarded. No confirmed signal of artificial origin has ever been received. The sky, at those frequencies, is full of natural sources, pulsars spinning with clockwork regularity, hydrogen clouds drifting between stars, the faint hiss of the cosmic microwave background itself, still cooling after nearly 14 billion years, but nothing that carries the unmistakable structure of intention, nothing that says, we are here, and we made this. There was one moment of ambiguity. In August of 1977, A radio telescope in Ohio recorded a signal that stood out sharply from the background noise. The astronomer who reviewed the data circled it and wrote a single word in the margin: "Wow." The signal lasted for the full 72 seconds. The telescope was pointed in that direction. It appeared to come from the constellation Sagittarius. Its frequency was close to the emission line of hydrogen, which some researchers had long suggested as a natural choice for interstellar communication. It has never been detected again. Dozens of follow-up observations have pointed instruments at the same region of sky. Nothing matching that signal has returned. Its origin remains unknown. It may have been a natural source not yet identified. It may have been terrestrial interference reflected in an unusual way. It may have been something else entirely. The data from that night is preserved, and the question it raises has not been closed, only set aside, unresolved, in the long catalog of things we do not yet understand. The silence continues. Some researchers have proposed that the silence may not be accidental, that civilizations capable of broadcasting across the galaxy might choose not to. The reasoning, in its starkest form, goes something like this. A universe old enough to contain many civilizations is also a universe in which resources are finite and the intentions of strangers are unknown. In such a universe, announcing your presence might not be wise. A civilization that has survived long enough to become truly powerful may have concluded, through whatever process of reasoning or experience, that silence is the safer posture. This idea is sometimes called the dark forest hypothesis, after the image of a forest at night where every creature moves quietly, aware that others are listening. It is a hypothesis, not a confirmed theory. It rests on assumptions about the motivations of minds we have never encountered, but it offers one explanation for the quiet. Not that the galaxy is empty, but that its inhabitants have learned, or decided, to be still. There is something almost melancholy in that image. A universe populated by civilizations that have each, independently, arrived at the same conclusion, that the cost of being heard is too uncertain, that the darkness is safer than the light, each one burning quietly, like a star behind clouds, present but invisible. And perhaps some have gone further still. Perhaps the most enduring civilizations are not the ones that broadcast, or build, or expand in ways that leave traces across the sky. Perhaps they are the ones that turned inward, or transformed into something that produces no signature we would recognize. Something that exists in a mode entirely outside our current understanding of what existence means. We do not know. The radio telescopes continue their slow survey of the sky. The frequencies scroll past, mostly empty, occasionally marked by the clean and indifferent signals of natural physics. And the question that Fermi asked over a quiet lunch, in a world that had only just learned to split the atom, remains open. Where is everyone? The universe offers no easy answer, only the expansion of space, the slow cooling of stars, and the long patience of time. All of it continuing, whether or not anyone is watching. And then there is another possibility, one that sits at the edge of what physics can say, and what philosophy quietly inherits. Some researchers have suggested that the civilizations we cannot find may not have gone silent by choice or by catastrophe. They may have changed. Not in the way that cultures change or technologies change, but in something more fundamental. A transition into a mode of being that leaves no thermal signature, no radio whisper, no gravitational footprint, something that, from the outside, would be indistinguishable from absence. We tend to think of advanced existence as an expansion outward, more energy, more structure, more reach across space. But perhaps that is only one direction. Perhaps the other direction, inward, quieter, more refined, is just as viable and leaves far less of a mark. A civilization that has learned to exist on vanishingly small flows of energy, or that has found ways to encode itself into the fabric of something we do not yet have instruments to read. We cannot rule it out, and we cannot confirm it. It remains one of those ideas that science holds loosely at arm's length, neither dismissing nor embracing. A shape in the fog. There is one more idea worth resting with before we move deeper into the physics of endings. It is not a mainstream scientific theory, but it is taken seriously enough by some physicists and philosophers that it deserves a quiet mention. The simulation hypothesis. The proposal that what we call the universe, the stars, the expansion, the slow cooling of everything, may be a computational process, running on some substrate we cannot access, in some context we cannot observe. And if that is true, then the end of the universe might not be a physical event at all. It might be something more like a process being stopped, a calculation reaching its conclusion, or simply being interrupted. There is no way, from inside such a system, to know every measurement we make, every observation, every equation we write down. All of it would be part of the process itself. The question cannot be answered from within. And so it sits, unresolved, in the same quiet room as the other deep uncertainties. Not something to dwell on, just something to acknowledge, the way you might acknowledge a door you have never opened. It is there, and the universe continues, regardless. Now, let the mind settle a little further. There is something in the physics of matter itself that deserves a slow, careful look. Something that most people have never heard of, and that even physicists hold with a kind of careful tentativeness. The possibility that protons decay. A proton is one of the fundamental building blocks of ordinary matter. Every atom in your body contains them. Every rock, every ocean, every star burning in the night sky is built, in part, from protons. They feel permanent. They feel like the kind of thing that simply is, without question, without end. But certain theoretical frameworks, grand unified theories, as physicists call them, suggest otherwise. These are attempts to describe three of the four fundamental forces of nature as different expressions of a single underlying force. And in some versions of these theories, the proton is not eternal. It is merely very, very long-lived. The predicted half-life, if proton decay occurs at all, is estimated to be at least 10 to the power of 34 years. That is a 1 followed by 34 zeros. The current age of the universe is roughly 10 billion years. 10 to the power of 10. So we are talking about a timescale that dwarfs the present age of the universe by a factor so large it resists any ordinary comparison. And yet, physicists have looked deep underground in enormous tanks of ultra-pure water, surrounded by sensitive detectors, shielded from the noise of cosmic rays. They have watched, patiently, for the faint signature that a proton somewhere in all that water might have quietly come apart. And so far, nothing. No confirmed proton decay has ever been observed. This is not a failure. Exactly. It is information. The absence of a signal tells us that if protons do decay, they do so more slowly than some of the simpler grand unified theories predicted. It rules out certain models. It constrains the theoretical landscape. And it leaves the question open, but narrowed. Perhaps protons are truly stable. and the theories that predicted their decay are simply wrong in that particular way. Perhaps they decay, but on timescales so vast that even our most patient experiments have barely begun to wait. We do not yet know. What we do know is this. If proton decay is real, then ordinary matter, the matter that makes up everything we have ever touched or seen, is itself temporary. Not on any timescale that touches a human life, or a civilization's life, or even the life of a star, but on the deepest timescales, the ones where black holes are still young. Matter itself would slowly dissolve. The atoms would come apart, not through heat or collision, but through the quiet, statistical inevitability of decay. And the universe would become a place where even the remnants of structure, the cold, dark spheres, the drifting fragments, would eventually lose their substance, becoming light and then less than light, becoming the faintest possible whisper of energy in an almost perfectly empty space. And threading through all of these possible endings, the heat death, the big rip, the slow evaporation of black holes, the decay of matter itself, there is a single quantity that determines which path the universe will take. Dark energy? That unnamed, unmeasured, deeply mysterious component that makes up roughly 68% of everything. The force, or field, or property of space, we are not entirely sure which, that is driving the expansion to accelerate. The fate of the universe is tied, more than anything else, to the precise nature of dark energy, and specifically to whether it is constant. Right now, our best measurements are consistent with dark energy being a fixed property of space itself, a cosmological constant, as Einstein first imagined it. Something that does not change as the universe expands. But the measurements are not perfect, and some models allow for dark energy that evolves, that grows stronger over time, or weakens, or fluctuates in ways we have not yet detected. If it grows stronger, the big rip becomes more likely. If it weakens or reverses, a big crunch becomes possible. If it remains constant, the long, slow drift toward heat death continues, patient and inevitable. We are, in a sense, living inside the answer to this question. The universe knows what dark energy is. We are still learning to ask the right questions, and there is something quietly humbling about that. All of our instruments, all of our mathematics, all of the accumulated effort of centuries of careful observation, and the single most important number for the fate of everything remains imprecisely known. Not because we have not tried, but because the universe is subtle. It does not announce its nature. It allows itself to be measured, slowly, partially, with effort. And it keeps its deepest answers in places that take generations to reach. So we continue. The telescopes turn. The detectors wait underground in their cold silence. The equations are refined, year by year, with each new observation. And the universe expands around all of it, unhurried, indifferent to our timelines, carrying its answer forward into a future so distant that the stars we see tonight will be long gone before it arrives. There is one more possibility worth holding gently before we let the universe go quiet. Some cosmological models allow for something called a big bounce. Not an ending, exactly, but a turning point. In this picture, a collapsing universe does not simply cease. It compresses, reaches some extreme density, and then rebounds. A new expansion begins. Not from nothing, but from the concentrated remnant of everything that came before. The mathematics behind this idea draws on quantum gravity, a field that is still being built, still incomplete. So the big bounce is not a settled prediction. It is more like a question the equations are willing to entertain, a door that has not been ruled out. What it would mean, if true, is difficult to hold in the mind. It would mean that what we call the Big Bang may not have been the first moment of time. It may have been a rebound, a universe before ours, collapsing inward, crossing some threshold we do not yet understand, and flowering outward again into something new. And if it happened once, it may have happened many times. Cycle after cycle, each universe expanding, cooling, perhaps growing dark, perhaps collapsing, each one giving rise to the next in a succession that has no clear beginning and no clear end. Whether anything passes between cycles, any information, any faint imprint of what came before, is one of the deepest open questions in cosmology. Some models say yes, that subtle traces might survive. Others say the bounce erases everything, and each cycle begins as fresh as if nothing had ever existed. We do not know which is true. And perhaps that uncertainty is appropriate, because the question of what came before the beginning is one that sits at the very edge of what physics can reach. For now, we can only note that the possibility exists, that the universe may be older than its own oldest light, that what we see when we look to the farthest edges of the observable cosmos may be only one chapter in a story without a known first page. Let that rest quietly for a moment. There is something else worth considering as we approach the end of this journey, something closer to home, in a way, something that touches not just the fate of the universe, but the nature of the experience you are having right now, lying still, drifting toward sleep. The arrow of time. You feel it constantly, though you rarely think about it. The sense that time moves in one direction, that yesterday is fixed and tomorrow is open, that a broken glass does not reassemble itself, that you remember the past and not the future. This directionality feels so fundamental that it seems like it must be built into the fabric of reality. But it is not, at least, not in the way you might expect. The fundamental equations of physics are, for the most part, symmetric in time. They work equally well, run forward or backward. A film of two billiard balls colliding looks physically plausible, whether you play it forward or in reverse. So where does the arrow come from? It comes from entropy. The universe began in a state of extraordinarily low entropy, everything concentrated, ordered, smooth, and from that starting point, disorder has been increasing ever since. Stars burning, galaxies spreading, heat flowing from warm places to cold ones, all of it moving, always, in the direction of greater disorder. And it is that gradient, that slope from low entropy to high, that gives time its direction. We remember the past because the past was more ordered. Causes precede effects because effects are the disordered outcomes of ordered beginnings. The arrow of time is not a law written into the equations. It is a consequence of where the universe started. Which means that as the universe approaches heat, death, as entropy approaches its maximum and the gradient flattens, the arrow of time itself begins to lose its meaning. In a universe at maximum entropy, there is no thermodynamic difference between one moment and the next. No process runs preferentially in one direction over another. The distinction between past and future, which feels so absolute to us now, would dissolve. Not because time stops, but because nothing changes. And if nothing changes, there is nothing to mark the passage of time with. No clock can tick if there is no energy to drive it. No memory can form if there is no structure to hold it. Time would still exist in some abstract sense, but it would be featureless and infinite, undifferentiated stillness. And yet, even in that stillness, the universe would not be entirely inert. Quantum mechanics does not permit perfect, permanent silence. Even in a void at maximum entropy, at temperatures indistinguishable from absolute zero, there are fluctuations. Tiny, random, momentary departures from uniformity. Particles briefly appearing and disappearing. Fields rippling without cause or consequence. These fluctuations are real. They are not theoretical conveniences. They have been measured. They leave traces in the early universe that we can still observe today. In the deep future, they would be all that remains. The last coherent structures in the universe would not be stars or planets, or even the cold remnants of black holes. They would be these quantum whispers in an otherwise empty dark, brief arrangements of particles that form for an instant and then dissolve back into the void. Most of these fluctuations would be simple: a few particles momentarily close together, a faint ripple in a field. Nothing that persists, nothing that accumulates. But over timescales so vast that no number in common use comes close to describing them, over spans of time written as 10 raised to a power that is itself 10 raised to a power, the mathematics of probability allows for something stranger. A Boltzmann brain. The idea was named after the physicist Ludwig Boltzmann, who thought deeply about entropy and probability in the 19th century. The concept is this: given enough time and enough random fluctuations, it becomes statistically possible, not likely, but possible, for a fluctuation to assemble something complex. Something as complex, in principle, as a functioning brain. A momentary conscious observer, arising from nothing, existing for an instant, aware, perhaps, of something, and then dissolving back into the void as quickly as it came. The probability is almost incomprehensibly small. The timescale required is almost incomprehensibly large. But in a universe that persists long enough, almost incomprehensibly small probabilities eventually become events. Whether such a thing would truly be conscious, whether it would experience anything in that brief flicker, is a question that physics cannot answer. It touches on the nature of mind in ways that remain deeply unresolved. But the possibility sits there, quietly, at the far end of time. A strange and solitary thought in an otherwise empty cosmos. And then, even that fades. The end of the universe is not a wall. There is no final moment, no last tick of a clock, no boundary where existence stops and something else begins. It is a gradient, a slow, patient dimming that unfolds across timescales so immense that the entire current age of the universe, all 13.8 billion years of it, would be invisible on the scale. A single point at the very beginning of a line that extends beyond any horizon we can imagine. The stars go out, one by one, over trillions of years. The last cold remnants cool further, over trillions more. The black holes evaporate, across spans of time that dwarf everything that came before. The quantum fluctuations continue, in the dark, for longer still. And somewhere in that unimaginable distance, the universe becomes something for which we have no word. Not dead, exactly. Not gone. Just very, very quiet. Dimmer than dim, stiller than still. Patient in a way that nothing alive has ever been patient. And perhaps that is the most honest thing we can say about the end of everything. It does not arrive. It simply continues to approach. And yet, even in that quiet, there are structures that outlast everything else. Black holes. Not the violent, Consuming things they are sometimes described as, but patient, enormously patient. The longest-lived large objects the universe will ever produce. A black hole does not burn. It does not radiate light in any ordinary sense. It simply holds, curving space-time so severely around itself that not even light, traveling at the fastest speed the universe permits, can find its way back out. And it persists. A black hole born from a collapsing star. A stellar mass black hole, perhaps 10 or 20 times the mass of our Sun, would take roughly 10 to the power of 67 years to disappear. That number is so large, it has almost no meaning in ordinary language. The current age of the universe is 13.8 billion years. Written out, that is a 1 followed by 10 zeros. 10 to the 67 is a 1 followed by 67 zeros. The difference between those two numbers is not a matter of degree, it is a matter of kind. And the largest black holes, the supermassive ones anchoring the centers of galaxies, some containing billions of solar masses, those take even longer. 10 to the power of 100 years. A 1 followed by 100 zeros. By the time the last supermassive black hole finally fades, the stars will have been dark for so long that the era of stars will seem, in retrospect, like a brief flicker at the very beginning of time. This slow disappearance was theorized by Stephen Hawking in the 1970s. The idea is subtle, and it emerges not from classical physics, but from the place where quantum mechanics and gravity begin to overlap, a place where our understanding is still incomplete. Near the boundary of a black hole, at the edge called the event horizon, quantum effects allow pairs of particles to briefly appear from the vacuum. Ordinarily, such pairs annihilate immediately. But near the event horizon, one particle can fall inward while the other escapes. The escaping particle carries energy away from the black hole. And over time, over immense, almost incomprehensible time, the black hole loses mass, slowly, steadily, until at last it is gone. This radiation is called Hawking radiation. It has never been directly observed. The signal from a stellar mass black hole would be so faint, so cold, so far below any instrument we have ever built that detection may not be possible in practice. But the mathematics, as far as physicists can tell, is sound. What happens at the very end of a black hole's evaporation remains one of the deepest open questions in physics. As the black hole shrinks, the radiation grows slightly warmer. The final moments, if they can be called that, would involve a release of energy, small by cosmic standards, but concentrated. And then, nothing. A region of space that once bent light and time around itself would simply no longer be there. What becomes of the information that fell in, the matter, the light, the structure of everything the black hole ever consumed, is a question physicists call the black hole information paradox. Quantum mechanics insists that information cannot be destroyed. General relativity, in its classical form, suggests it can be. These two frameworks, each extraordinarily well-tested in its own domain, disagree here. The resolution is not yet known. But let us approach the horizon more slowly. Imagine falling toward a black hole, not violently, but gently, from a great distance, drifting inward along a long, curving path. Far away, the black hole would be invisible against the dark. You would know it only by the way light from distant stars bent around it, forming rings and arcs, a gravitational lens, curving the paths of photons that pass too close. As you drew nearer, time itself would begin to change. This is not a metaphor. General relativity predicts, and experiments confirm, that gravity slows the passage of time. The stronger the gravitational field, the more time dilates. Near a black hole, this effect becomes extreme. To an observer watching from far away, you would appear to slow as you approach the event horizon. Your movements would grow sluggish. The light reaching them from you would stretch to longer and longer wavelengths, shifting toward red, then infrared, then radio. You would appear to freeze at the horizon, growing dimmer and dimmer, never quite crossing, at least not in the time of the distant observer. But from your own perspective, you would notice nothing special at the moment of crossing. The event horizon is not a surface. It has no texture, no wall, no marker. It is a boundary defined entirely by geometry, the point beyond which the future, in every direction, leads only inward. Once inside, there is no path that leads back out, not because something blocks the way, but because space-time itself is oriented inward, every direction, including what would ordinarily be called time, points toward the center. For a large enough black hole, the tidal forces at the horizon, the difference in gravitational pull between your head and your feet, would be gentle enough that you might not feel them at all as you crossed. For a smaller black hole, those tidal forces would be severe. The technical term, offered without drama, is spaghettification. The gradient of gravity would stretch a body along the radial direction and compress it from the sides, drawing it into a long, thin strand. Inside the horizon, the singularity lies ahead, not in space, but in time. It is not a place you could avoid by steering around it. It is a moment in your future, as inevitable as tomorrow. What the singularity actually is, physics cannot yet say with confidence. General relativity predicts a point of infinite density, infinite curvature, a place where the equations break down entirely. But most physicists believe this breakdown reflects the limits of the theory, not a true feature of nature. A complete theory of quantum gravity, which does not yet exist, would likely replace the singularity with something finite, something describable. What that something is remains unknown. String theory, loop quantum gravity, and other frameworks each offer different suggestions. None has been confirmed. This is one of the places where the map of physics ends and honest uncertainty begins. What we can say is this: the black hole is real. The event horizon is real. The slowing of time near massive objects is real, measured in GPS satellites and atomic clocks and the light from distant stars. The evaporation through Hawking radiation is as real as the mathematics that predicts it, even if we cannot yet observe it directly. And the end of the last black hole, whenever it comes, across that unimaginable span of 10 to the 100 years, would leave behind only a thin, cold breath of photons and leptons, spread across a universe so vast and so empty that the distance between any two particles would be, for all practical purposes, infinite. After that, the universe would contain almost nothing. Not nothing in the absolute sense. Quantum fields would still exist, humming at their lowest possible energy. Space would still expand, carrying that near nothingness further apart with every passing moment. The temperature would be so close to absolute zero that the difference would be, in any practical sense, unmeasurable. This is what physicists mean by heat death. Not heat in the ordinary sense, not warmth, but thermodynamic equilibrium. A state in which every region of the universe is the same temperature as every other. A state in which no energy can flow from one place to another, because there is no difference left to drive the flow. No difference. No gradient. No work possible. Just an immense, dark, nearly featureless expanse, cooling toward a stillness that approaches but never quite reaches the absolute. And in that stillness, time continues. And yet, time continuing means very little when there is nothing left to mark its passage. No clocks, no oscillating atoms, no light crossing from one place to another. Time, in any meaningful sense, is something that happens between events, and in a universe approaching heat death, events themselves become vanishingly rare. There is a concept in thermodynamics called a fluctuation. Even in a system at equilibrium, particles do not sit perfectly still. They shift, ever so slightly, in random directions. Most of these shifts cancel out immediately, but occasionally, by pure chance, a small region of space will arrange itself into something slightly more ordered than its surroundings. A brief, local decrease in entropy paid for by the vast surrounding sea of disorder. In an ordinary universe, these fluctuations are too small to matter. But in a universe that has been sitting at near maximum entropy for long enough, and we are speaking now of timescales that have no name, timescales written as 10 raised to the power of 10 raised to the power of 56, the improbable becomes, eventually, inevitable. Over such spans, random quantum fluctuations could theoretically assemble something stranger than a star, stranger than a galaxy. They could assemble a mind, not a mind that grew from biology or from any process of evolution, but a momentary arrangement of particles that, for just an instant, constitutes something like a conscious observer, a structure with memories, with the sensation of existing, with perhaps the feeling of waking, and then, almost immediately, dissolving back into the void. Physicists call this a Boltzmann brain, after the 19th century physicist Ludwig Boltzmann, who first explored the deep implications of statistical mechanics and entropy. It is not a comfortable idea. It raises quiet, unanswerable questions about the nature of experience itself, about whether any given moment of consciousness is a genuine product of a long history, or simply a fluctuation, a brief island of order in an ocean of randomness. Most physicists believe we are not Boltzmann brains. The reasoning is subtle and rests on the structure of our observations being far too coherent, far too consistent with a low entropy past, to be the product of a random fluctuation. But in a universe old enough, patient enough, the question loses its footing. There is no one left to ask it. And so the universe drifts, not toward anything, not away from anything, simply continuing in the way that a system at equilibrium continues, without direction, without narrative, without the thermodynamic arrow that once gave time its sense of flowing forward. That arrow, the deep asymmetry between past and future that we feel in every moment of our lives, is itself a consequence of the universe having begun in a state of extraordinarily low entropy. The Big Bang was not just an event of immense energy, it was an event of immense order, and everything since, every star that burned, every wave that broke, every thought that formed and faded, has been the slow, patient unwinding of that original order. In a universe at maximum entropy, that arrow dissolves. Past and future become, in a thermodynamic sense, indistinguishable. Time does not stop, but it loses its direction. And the universe that remains, if we can still call it a universe, is one in which the very concept of before and after has become, at best, a local and temporary illusion. There are other possibilities, held more loosely, spoken of more quietly in the literature. Some cosmological models allow for what is called a big bounce, a scenario in which a collapsing universe does not end, but rebounds. in which the compression of a big crunch reaches some minimum scale and then reverses, seeding a new expansion, a new low-entropy beginning. Current observations do not favor a collapse. The expansion is accelerating, not slowing, but the data does not close every door. Roger Penrose proposed something he called conformal cyclic cosmology, a framework in which the far future of one universe, stripped of all massive particles, all structure, all distinction, becomes mathematically equivalent to the beginning of another, in which the heat death of one cycle is, in some deep geometric sense, the Big Bang of the next. In Penrose's model, faint traces of the previous cycle might be encoded in the cosmic microwave background, subtle patterns, rings of slightly different temperature, left by the last evaporating black holes of the universe before ours. Whether those patterns are truly there remains a matter of careful, ongoing debate. But there is something quietly moving about the idea that the end and the beginning might be the same moment, seen from different sides. And then there is the possibility that none of this unfolds as described. Vacuum decay, the hypothesis that the Higgs field may not be in its true lowest energy state, would not wait for entropy to do its slow work. A bubble of lower energy physics, nucleating somewhere in space, would expand outward at the speed of light. Inside that bubble, the fundamental constants of nature would be different. Atoms as we know them could not exist. The bubble would carry no warning ahead of it, because nothing travels faster than light. One moment, the universe as it is. The next, something else entirely, propagating outward in all directions, restructuring everything it touches. Current measurements of the Higgs boson mass suggest the vacuum may indeed be metastable, though the timescale for such a decay, if it occurs at all, is thought to be enormous, far longer than the current age of the universe, perhaps longer than the age of many universes placed end to end, as far as we can tell. And that phrase, as far as we can tell, is perhaps the most honest thing physics can offer when speaking about the end of everything. We measure what we can reach. We model what we measure. We extrapolate, carefully, into the dark beyond our instruments. And we hold our conclusions with the appropriate looseness, knowing that the universe has surprised us before and will again. The observable universe is about 93 billion light-years across, and it is only a fraction of what exists. Beyond our cosmological horizon, space continues, perhaps forever, carrying regions we will never see, never measure, never know. In roughly 2 trillion years, the galaxies we can currently observe will have receded beyond that horizon entirely. Future observers, if any exist, will find themselves in a universe that appears to contain only their own local group of galaxies. No evidence in the sky that anything else ever existed. The universe does not announce its own scale. It simply is. And what it is, at its largest and its longest, is something that resists the ordinary instruments of the mind. Not because it is beyond understanding, but because understanding takes time, and the universe has more of it than we can hold. The end, if it comes, and in some form, as far as we can tell, it will, is not a wall. It is a gradient, a slow, patient dimming, spread across timescales that have no names. The last black hole releasing its last faint breath of radiation into a cold and empty dark. The last quantum fluctuation assembling something briefly and then letting it go. The last distinction between one region of space and another, fading, until there is no difference left to measure. No gradient, no flow, just the quiet, continuing.